Okay, I'll try to be quick. This is the last presentation of the school, and I know we are late, so I'll try not to take too much time from the break. So thank you for the introduction. As Visily introduced, my name is Michela Testolina. I am a researcher at IIS, and my field is mainly image coding. In the past, I worked a lot actually on simple image coding, and in the last few years, I've been working on image coding for storage on DNA. So what we'll be talking is especially about the standardization of image coding into DNA. Okay, as I said, I'm going to be talking about standardization, and most of my academic career, I've been involved into the JPEG standardization. So what is the JPEG standardization? So it's a group that is a joint committee between ISO, IEC, and ITU, and brings together experts from industry and academia to define the next generation image coding standards. So it's basically a group of experts on image coding that gather together and try to define new standards for image compression methods. So inside the JPEG standardization group, there is, there's different groups working there, and one of them is about JPEG DNA. I will be talking about the JPEG DNA's activities and what it's happening there. I'll start from the scope of the activity. So the scope of JPEG DNA is the creation of a standard for efficient coding of images that considers biochemical constraints and offer robustness to noise introduced by the different stages of storage process that is based on DNA synthetic polymers. So this is just a very background on standardization, and I'll now start from the motivations, especially related to image coding into DNA. And I usually like to start from this art installation from Eric Kessel. So it's called 20 Hours in Photos, and the artist decided to print the number of pictures that in 24 hours were uploaded on social media. In particular, they are coming from Flickr, Facebook, and Instagram. So of course, they printed only the publicly accessible images, but yes, that's how they look like. So this is 24 hours of pictures printed and put in a room. And I think this gives an idea of how many images are actually there, how many images are stored, taken, stored, and shared on social media. So here in numbers, so we have the numbers of photos that are taken every year. Is estimated to be around 2 trillion next year. Of course, along with that, people are going to need to store these pictures, so it's estimated that it's going to be around 13 trillion in 2026, so next year. Okay, I stole this idea from Aline. She presented something similar, but it's my phone. It's an iPhone 11. So maybe we can compute how much space these images would take. So when I go and see the resolution in terms of pixel on my phone, it's about 4,000 by 3,000. So this is the total number of pixels. Of course, images are stored in 8 bits per channel, and we have 3 color channels. So we have these many bits. We convert to bytes. So we arrive to about 36 megabytes for an image. We saw in the previous slide that we have about 13 trillion images that are expected to be stored next year. So if we multiply this by 13 millions, we have 468 zettabytes, so it's 468 billion terabytes. Of course, when I store an image on my phone, I don't store all the information, so there's something happening. In fact, when I go and see the file size of the image is actually 1.2 mega. So what is happening here, probably most of you know, so there's something called image compression. So image compression is essential to reduce the storage space consumptions. There's 2 types of compression. There's lossless, which is something similar to what you probably use as a zip file. but specific for images, or there is lossy compression, which is able to achieve higher compression, but it decreases the visual quality. For example, this image is 1.5 megabyte on my computer, and then when I compress it, I can arrive to 10K, but of course you see that the image is highly degraded. In the context of this presentation, we will talk about lossy compression. So the field of image compression is not a new field in the state of the art. There's a lot of research that have been done on it, and there's a lot of standards that have been presented. Probably all of you know the JPEG standards and probably use it on a daily basis. Actually, it's a very old standard. It was standardized in 1992. Still, it's one of the most used standards for image coding. We have in the presentation early from Ina, we have mentioned about JPEG 2000. It was used in the past for storage on their system. Probably you have heard, well, on my phone in this slide here, you have HIF here, so that's the format that my phone is using for storing picture, which is actually related to this HEVC standard here. If you have a new iPhone, you probably use JPEG XL, and the JPEG activity is actually working, well, it already published the first AI-based image compression method, which is JPEG AI, which is a new standard for this year. So there's a lot that have been happening in image compression, classical image compression, just in binary. So you remember that this is what I show you. So there's a lot of images out there, and for sure image compression helps, but the question is, can we do better? And I mean, of course, we all know the answer. Yes, there's some other methods that will allow us to compress images using DNA. I will not go through all the advantages and disadvantages because we heard them a lot throughout this school. So I will just give you an introduction on how DNA-based image coding is done. So I will present two main pipelines for compressing into DNA images specifically. The first one is what I call binary-based image compression. So we saw that there's a lot that have been done for image compression. So this approach consists in taking, let's say, an image, using a binary compression method. It could be one of the standards that we saw before. To get a compressed bit stream, and then use any quaternary coding method, so anything that will allow us to go from binary to quaternary, so obtaining a FASTA file, and then we can do synthesis and sequencing, and then do the opposite. So we get our FASTA file, do quaternary decoding, we get our bit stream, and then do binary decompression. So this also allows us some flexibility. So if we already have some encoded data, for example, if we have a file that has already been compressed with JPEG because you already stored and you already have your compressed bitstream, you can skip the first part and go directly here, so you can do the same process as before. There's another way of doing this. So basically, instead of doing the compression in binary and then doing quaternary, we can go directly to quaternary compression, so to have just one block here that allow us to do compression of the image and go directly on DNA instead of passing through the binary. So this is just a different approach. So I wanted to summarize these two approaches. So we have the binary based. As I said, there's a lot that have been done for image compression, so we can use any of these methods for compressing the image, and then there's also a lot that have been done for going from binary to quaternary, so it's just putting together these two methods, or going directly to DNA. In this case, this field have not been, is an emerging field, so there's actually not many methods in the state of the art that presents this approach. So since there's a lot of availability of methods that are already well established and commonly used in this approach, the JPEG DNA standard decided to go for this approach, and that's what I'm gonna present you here. So this is a high-level overview of the JPEG standard. So if we take our uncompressed image, we can go to, we can compress it first to binary and then we go to quaternary. So the compression is done with JPEG XL. So it's, I presented you earlier, it's a standard method that was standardized in 2021. And then we go from the binary stream to the quaternary by using a DNA Raptor encoder. So we obtain our FASTA file, we're going to DNA and then going back through the opposite way. So this allows us some flexibility. For example, we can consider even more advanced methods than JPEG XL. I mentioned earlier that this year the JPEG AI standard was released, so there's another method. So for example, this pipeline will allow us to use, for example, JPEG AI or any other methods that will be standardized in the future instead of JPEG XL. The JPEG DNA standards allows consider some biochemical constraints, and the ones that are considered currently by the activity is the strand length limitation. So we are synthesizing up to, well, it generates up to 300 nucleotide oligos. We have maximum 3 repetition of the same nucleotides for the homopolymer run. We have a GC content between 40 and 60%. And also will prevent the repetitive motifs of size 3 to 5. So another thing about the JPEG DNA standards is that it is done in a way that if in the future we would like to use different constraints, because maybe the technology changes, they can be changed. So if there's new constraints or they just need to be changed, the standards allow us to easily change this. So here are some results in terms of ray distortion curves. So when we want to measure the performance in image compression, we do these kind of curves. On the bottom axis here, we have the nucleotide rate, which is the number of nucleotides divided by the total number of pixels of the image. And here we have a measure. Here we have the PSNR, so it's based on the pixel by pixel difference between the original and the reconstructed image. And we have 2 more metrics here, MSSIM and VMAF, which actually correlate a little bit better with the human vision. But what this says basically is that the higher the curve, the better the performance of the compression method. So here I'm actually comparing, let me move this one here. So we have an anchor, which is in blue, which is a method. It's not really a fair comparison because it's a method based on JPEG, but it's what we use for the comparison during the JPEG DNA call for proposal activity. And then we have the JPEG DNA standard with JPEG XL in orange, and then with JPEG AI in green. So the idea was, okay, this is the standard with JPEG XL, which already does better compared to what we consider the anchor method during the activity. But we can use even other methods, for example, JPEG AI, which at the lower parts of the spectrum give us an additional advantage. So here is to give you a quick visual comparison of the images. I think you can see probably only a little bit or maybe not at all. So here we have the original image. This is a crop, so this is not the full image. And this is the image compressed with the JPEG DNA standards using JPEG XL. And this is the same using JPEG AI. So the target range of bit rates of the JPEG DNA activity is very high quality. That's why it's very hard to see the difference between the images, since it is for long-term storage, and usually that's what we want, very high quality. It is you're actually able to notice. I don't know if here probably a little bit if you have good vision. The original part, if you take the texture of the skin, we see that for JPEG XL and for JPEG AI is different. And also the texture of the skin between these two is actually different. It's very hard to say which one is better, but there's a difference. So as I said, we are in the extremely high quality range since we want to target long-term storage. This is another image. So we see some texture of the feathers that for the two birds is different. It's hard to see here. I think that in some parts the JPEG AI standards tend to reconstruct this specific texture a little bit better than JPEG XL. But as I said, the difference is really minimal, and in this type of screen you're not even able to see. The results that I presented are, well, let's say the JPEG DNA standard does not consider any type of oligo formatting, making it suitable for wet lab experiments. So what the JPEG DNA standard does is only encode the payload. So all the ray distortion curves I presented you earlier were actually by encoding only the payload. So we know that if we want in real life to encode this information, we were gonna need some formatting. So we are gonna need to add some primers, some index, and to have some kind of redundancy for making it robust to errors. So when we add all this information, actually you see there's the shift. So in orange is without error format, without wet lab formatting, and in green is with wet lab formatting. We can see, of course, we are gonna lose a little bit in terms of performance, but still we are above the method that we consider as an anchor. Okay, now I have a part that is about error resiliency in image codec specifically. So we saw these slides is actually from Serge. I took a screenshot from his presentation. And in the context of this school, we saw a lot of error correction mechanisms that can be applied into the field of DNA storage for making it robust to errors. We saw clustering and consensus with Dominique, and we saw channel coding with Serge. So what I want to say in this part of the presentation is, of course, not to substitute any of these parts. So we still need to have clustering consensus and channel coding. But the idea is, what about in the image coding part, we add some error resiliency features, which for any reason, any of the mechanisms that we had before fail, we are still able to decode our image and we don't lose all our data. So this is just to add one additional layer of protection. So JPEG XL and JPEG AI are coded in a way that even if in the bit stream there is 1 bit difference compared to the original, so if there is any error happening there, you're going to lose your whole file and you're not going to be able to recover your image. But there's other standards, for example, the JPEG 2000 standards that allow some error resiliency features. So it's not going to be able to fix this error, but at least you're going to get something, a noisy version of the image. So this is an idea that maybe it's interesting to explore in the context of JPEG, in the context of DNA compression. So what I did is I changed a little bit the pipeline of JPEG DNA. So instead of using JPEG XL or JPEG AI, I'm using JPEG 2000 here. And then when I get my FASTA file, I just go inside the FASTA file and change. So I'm considering only substitution errors, 1, 2, and 3 errors. So I randomly change 1, 2, or 3 nucleotides in the file. And this is what I get. So this is the original image. This is the file compressed with JPEG 2000 and applying 1 substitution error. You can see that I'm able to recover my image. My image is not perfect. You can see here that there's some distortion, some kind of noise that appears here. But let's remember that with JPEG XL, we would not have been able to decode anything at all. We have an example with 2 substitution error, same thing. We are getting some noise in the image, but we are able to get the image. 3 substitution errors, again, we have some noise in this part. And I saw that when I apply 4 substitution errors, there's no way of decoding the whole file. So that's it. This was supposed to be just a quick presentation about the field of image compression and standardization related to storage on synthetic DNA. So the JPEG DNA activity is working into the integration of error correction mechanism, and actually we are planning a wet lab experiment to validate the JPEG DNA standard and pipeline. So if there is any conclusion I would like you to take home from this speech is that every year there's trillions of images that are captured by devices. So this makes the field of archiving, image archiving, an ideal use case for DNA data storage. So there's standardization going on for the specific case of image coding into DNA, which is represented by the JPEG DNA standards. And then as a future research activity, also considering this robustness to noise in different way, it's very important. So this concludes my presentation. Thank you. Maybe we want to take the questions during the coffee break. Okay? Thank you.